Okay, so this is a solution to exercise 2.2, question 6. So just going to give you a bit of time to read the question and pause the video in case you want to have a go before I explain how to do it. Right, so hopefully you've had a chance to pause the video and read the question. So let's start with part 1. We have got this matrix and we want to find an expression for the inverse in terms of k. Alright, so I'm gonna get another piece of paper here just to give me plenty of space. Now, the first thing that I want to do, if I call this matrix M, is work out the determinant. Alright, so I'm going to expand this along the first column because I think that's going to be the easiest. So I've got my first part here, k, then if I cross out those two I have to find the determinant of what's left. So that's going to be 4 minus 9, so 4 plus 9. Then my next part, remember I have to have a minus sign, then it's going to be 2. Then crossing that row and that column, we've got 14 minus 12, so 14 plus 12. Then my third one, it's going to be positive again. I've got 1, crossing that row and column, minus 21, minus 8, so plus 8. And simplifying that down, I've got 13k minus 52. 6 times 2, and then that's minus 13. So overall, 13k minus 65. Alright, so that's the determinant. I'll leave it as that for now, and then I want to continue and find the inverse. So to find the inverse, I need to find all the cofactors, so that's taking each individual cell. If I cross out that row and column and find the determinant of what's left, pretty much what I did here, but for every single cell in the matrix. So I like to, well, the common way of writing this is with capital letters, so I like to write them all out first and then put them into the matrix. So we'll start with A1, which is what you get when you find the determinant after crossing these out, so that's that 13 over here. A2 is what you get there, so that's this one, 26, or minus 26, because we remember that minus sign is actually part of it. Then A3 is going to be your minus 13. Okay, then let's do the B's, so that's the second row. So B1 is going to be, if we take that row and that column out, what's the determinant? Minus 4, minus 3, and that whole thing is negative because of the pattern of the signs. We go plus, minus, plus, minus, plus, minus, and so on. Okay, so B2 is this one, we cross that out, minus 2k minus 4, B3, cross this one out, we end up with 3k minus 8. Remember there's a minus on the outside. Now doing the last one, C1 is going to be crossing this, so minus 6 plus 2. C2 crossing this row and this column, I've got so minus on the outside and then minus 3k plus 7. And then C3, I've got minus 2k plus 14. Now writing all of this into the inverse, M inverse equals 1 over the determinant and then I need to write all of these numbers in. Remember that we switch the row and the column, so these are going to now be the top row instead of the first column. So we've got 13 minus 26 minus 13, and here we've got 7. Here we've got minus 2k minus 4. Here, expanding this out, we've got 8 minus 3k. Then this is going to be the last row. That's going to be minus 4. That's going to be expanding out 3k minus 7. And that's going to be 14 minus 2k, just writing it a bit neater. Okay, so that's the inverse in terms of k. Then we also need to state the value for which these planes would not intersect in a unique point. So the coefficients here are all the same as the matrix, so these would not intersect when that matrix is singular. Which means that the determinant of m is 0, so 13k minus 65 equals 0, which means 13k equals 65, 65 divided by 13 is 5, so k would be 5. So they would not intersect at a unique point when, so yeah, I should say wouldn't intersect at a unique point when k equals 5. Okay, so now let's try and move on to part 2. So to make this easier, I've tried to make a sort of reveal here of what we need for reference. Not the most elegant thing ever, but it's worked okay. Alright, so there's the inverse, exactly what we just worked out, and there's our value of k for which they do not intersect in a unique point. So we can then carry on with part 2. So I want to describe the intersection of these planes. Well, we can see that most of the coefficients there are the same as what's in this matrix, except for k equals 4. Now that's not this value, so that means that they are going to intersect in a unique point. So what we need to find is actually what is that unique point, and we need to find it in terms of p as the question asks. So we can rewrite this into a matrix equation. So we have got 4 minus 7, 4, 2 minus 2, 3, 1 minus 3 minus 2. And that's multiplied by x, y, z. And that's equal to p1, 2. So to find out the values of x, y, and z, which will be the intersection point, we just need to multiply both sides of the equation by the inverse of this matrix, which we know it does have, because the determinant doesn't equal 0 when k is 4. So we can actually just use this straight away. We could get a calculator to work it out, but since we've got this already worked out, just subbing in 4 is probably going to be even quicker than typing it into the calculator. So that will leave us with x, y, z. We know if we multiply this by the inverse, then we're going to end up with an identity. We'd just be left with x, y, z. And then we need to multiply the matrix at the front. Remember, multiplication is not commutative, so make sure you do it at the right side. So we'll leave our determinant. 13 times 4 take away 65 is going to be negative 13. Then subbing in here, the ones which are numbers will just be the same. So that's why I say it's really quite quick. So we've got 13 minus 26 minus 13, those all stay the same. 7. Okay, subbing in 4 here, minus 8 minus 4 is going to give us minus 12. Subbing in 4 here, 8 minus 12 gives us minus 4. Then here we've got minus 4, that's the same. So then 12 minus 7 gives us 5. And 14 minus 8 gives us 6. Then we're just going to multiply that whole thing by the p1, 2. Then we want to multiply that out. Leave the minus 1 over 13 at the front to begin with. And we're going to get 13p minus 26 minus 26. Then here we're going to get 7p minus 12 minus 8. And at the bottom we're going to get minus 4p plus 5 plus 12. Simplifying this, we will have 13p minus 52, we will have 7p minus 20, and minus 4p plus 17. Okay, then we can finish off by writing our quick sentence explaining what's going to happen. So the planes intersect at, and we want to write this as a coordinate. Yes, it will be a messy coordinate, but that's fine. 13p minus 52 over minus 13, the x coordinate. 7p minus 20 over minus 13, that's the y coordinate. And minus 4p plus 17 is minus over 13 over minus 13. So the coordinate, and that's our coordinate of intersection. Okay, and that is your answer to part 2. Alright, so I don't think we need this to answer part 3, so I'm just going to put this to one side. And now let's look at what's part 3. So find the value of P for which these planes have at least one point of intersection, and describe the arrangement of the planes geometrically in 3 dimensions. So again, most of the coefficients are the same, but this time k equals 5. Now we remember from part 1, k equals 5 means that the planes do not, well, mean that this matrix is singular, which means that these planes would not intersect in a unique point. Okay, but we want at least one point. No unique point doesn't mean no point at all, because remember there's still the possibility that they could intersect in an infinite number of points, which is that situation where the equations are consistent and we have a sheaf. So that's what we want to try and do here. We want to solve these 3 equations simultaneously in order to find that those conditions for it to be consistent and for it to be a sheaf. So we want to try and start eliminating something. So let's label these equations for clarity 1, 2, and 3. So what can we try to eliminate here? Nothing looks particularly easy, so let's just eliminate x. So to do that, I can do, well, yeah, because there's just one x there, that will work. I can do 1, and I can take away this number 3 multiplied by 5. That's going to work. So that's going to be 5, take away 5x, yep, which eliminates x, and then negative 7y plus 15y, which is going to give me 8y. Then I'm going to have 4z plus 10z, gives me 14z. Then I'm going to have p minus 10. Okay, then, so that's one equation without x. So then let's do 2 and 3. Let's do 2, take away 3 times 2. That's going to work as well. So 2x minus 2x works. Negative 2y plus 6y is going to give us 4y. Then 3z plus 4z is going to give us 7z. Then 1 minus 4 gives you minus 3. Now, to make them the same on the left-hand side for ease of comparison, we can just multiply this one by 2. So that's going to be 8y plus 14z equals negative 6. And you can see now, if we ignore that one, the same on the left-hand side. So for it to be consistent, they need to be the same on the right-hand side as well. So this is consistent if p p equals 4, in which case the planes intersect along a straight line with the equation 8y plus 14z equals -6, forming a sheaf. So it's good to use those keywords.